Hello guys, welcome to this new video. Now we're going to go through question 9 in the 2025 Specimen Paper 2. So we have this diagram here showing two parallel plates oppositely charged, and firstly we need to show the electric field lines due to the charged plates. So what we need to remember is that electric field lines always point in the direction a positive point charge would move. So let's imagine we put a positive charge over here, and let's think which way would it move. Well, I think it's quite obvious that it would move down towards the negative plate, as it is attracted by the negative plate and repelled by the positive plate. So the field lines will look like this, as these lines just show the direction a positive point charge would move. And then we have this edge effect, which we don't need to learn too much about in IB. We just need to remember that this happens. So when we don't have like infinitely long parallel plates, on the edge the fields kind of curve around. And this is pretty much all we need to know about this phenomenon. We don't need to calculate with it or explain it. It's just really something we need to remember. And that's also why we get 2 marks, one for the correct direction and one for the edge effects. Then we are told the potential difference between the plates is 960 volts, and the distance we're also given. We need to calculate the electric field strength. Well, we have this very useful formula, V is equal to E times D. So E is equal to V over D. So 960 divided by 8 times 10 to the minus 3 meters. So that will give us 1.2 times 10 to the 5 volts per meter, or we can also say newtons per coulomb, as electric field is also defined as force per unit charge, or the potential over the distance. Both are accepted units. And then we have this experiment where we have an oil drop, and we introduce this through a narrow tube. And yeah, so it falls through this air over here before falling between the plates, and we need to explain why this oil drop becomes charged. And well, why it becomes charged is because it has a little bit of friction, so it coincides, it hits these walls of the tube, and through friction charge is being transferred to the drop. So collisions with wall, and so friction transfers electrons. And then we can note that this transfer happens both ways. So it's not like the electrons only go from the tube to the oil drop. If the oil drop has a larger, more electrons, then the charge will go from the drop to the walls. It happens both ways, but this is how it can become charged. And then we have this oil drop stationary between the plates, and we have buoyancy on the drop, and we're also told that the density of the oil is 730 times greater than that of air. We need to show that the buoyancy force is much smaller than the weight. So we need to remember some formulas here. Well, first of all, the simplest one is weight is equal to mass times g. But we don't really know the mass of anything. We don't know the mass of the drop, so it would be ideal to replace that with something. And well, we can, as we know that density is mass over volume. So from this, we see that mass is equal to density times volume. So we can very nicely substitute this in. And so we get that the weight of the oil will just be the density of the oil times g times the volume of the oil drop. And so this is how you can calculate the weight force acting on the oil drop. And we also know that the buoyant force is just the weight of the displaced liquid. So when we calculate the mass, we don't take the density of the drop, rather we take the density of the displaced liquid. So we'll have the density of air times g times the volume of the drop. The volume of air being displaced is still the same as the volume of the drop, as those two are identical. And then we need to calculate this ratio of the buoyant force to the weight force. So we can plug in the formulas we just derived, divided by rho oil GV. We see that the volume is the same for both, or we can also cancel G. So we see it's the density of air divided by the density of the oil, but we know density of oil is 730 times greater than the density of air. So we know that the ratio is 1 to 730, and this is 1.4 times 10 to the minus 3. So from this, we can see that the weight is much, much larger than the buoyant force, and it's a very small number. Now we need to draw the forces. Well, we know that we have the weight force, gravity acting on it, or just Fg or W, and well, we know it's stationary, and we know it's charged, and it's in between charged plates. So through this reasoning, we also know there also must be an upwards electric force, and these two have equal lengths because our drop is stationary, and if it's stationary, it means that the net force must be 0. F net equals 0, and so they cancel each other out. And this is also the reason why this electric force must be pointing upwards, as if it would be pointing downwards, then there would be no way for these two forces to cancel each other out, to balance one another. And then we need to show that the electric charge on the oil can be given by this relationship. Well, we can use the fact that the net force is 0, so the gravitational force will be equal to the electric force, and we have very simple formulas for this. So we know the gravitational force is m times g, electric force is q times e, charge times the electric field, and we know the mass is just, as we calculated in the previous one, is just the density of the oil times the volume of the drop times g equals to QE, and we just need to divide by E to find the final relationship. Like this. And we need to state the sign on the oil drop. Well, it's going to be negative, because if we imagine a droplet in between these plates, we know that the electric force is acting upwards on it. So if there's an electric force acting upwards, it means that it's attracted to the positive plate, and therefore it must be the negative charge. Otherwise, if it would be positive, then the electric force would just be in the direction of these arrows, as these arrows give us the direction of a positive charge movement in a plate like in between two plates like this. So that's why it must be negative. And then we are told that the electric field is now turned off, and it drops, reaching a constant V, and we need to outline why this relationship holds. Yes. Well, constant velocity means that we have an acceleration of 0. A is equal to 0, as we are not accelerating anymore. And from this, it follows that the net force will also be 0. And well, the two forces we have, no longer electric field as it's turned off. So we just have the drag force being equal to the weight force. Drag force is just a resistive force, so it acts in the opposite direction to our velocity. So if our drop is falling downwards, mg is like this, v is like this, then the resistive force must be acting upwards to try and oppose the motion. And well, from our data booklet, we see that the drag force is just 6 pi times r times v, and the weight, well, again, it's just m times g, but we know that m is just the density of the oil times the volume of the oil times g, and that is the relationship we needed to come up with. And then we need to show that this is the charge on the oil drop given these numbers. And well, we know that the charge can be calculated by the density of the oil times g times v over e. So this is what we deduced all the way up here. And yes, so they're the same. And then now we know that this part over here can just be calculated with the drag force, as they are equal. So these two are the same. So we can replace these two. So we can say that this will be 6 pi r rho r v divided by e. And now we just need to plug everything in and we should get the correct answer. So 1.6 times 10 to the minus 5 times 1.36 minus 6, 1.4, 10 to the minus 4. And it's all divided by 1.2 times 10 to the 5. We calculated this all the way up here. So it's worth remembering what you did in the question previously, as often we need to use numbers we calculated before. And from this we get 4.79 times 10 to the minus 19 coulombs, which is indeed approximately 4.8 times 10 to the minus 19 coulombs. And then we are told that this oil drop splits into two parts of equal mass, both are charged. Deduce the net charge on each part. Well, what we need to really remember here is that charge is quantized. So what this means is that whenever something has a charge, it must always be an integer multiple of the standard charge. So 1.6 times 10 to the minus 19, that's e. So it must be a scalar integer multiple, so 1e, 2e, 3e, so on. And it cannot be, so that means it cannot be like 1.5e or 4/3e or whatever. That wouldn't mean it's quantized. So they must be integer multiples of e. And well, we know that both are charged, and we also know that before, well, this is just 3e. This is 3 times 1.6 times 10 to the minus 19 coulombs. So we know in total we have 3 e's, so 3 electron charges. And we also know that when they split up, the charge must be conserved, as we don't introduce any new charge to the drop. And we know that both are charged, so both have a charge of non-zero. So the only way that's possible is if one has 1e and the other has 2e. As like this, their sum is still 3e and they're both integer multiples of e. We couldn't say like 1.5e and 1.5e, as even though they have the same mass, we might think 1.5 and 1.5, but the charge must be quantized, so 1.5 is not an integer, so that would not work. And well, this was the end of question 9 in this 25 specimen paper. I hope I was able to help, and see you in the next video.